just like this morning, I forgot to press record. Okay, so that's kind of where we ended off with the atomic theory, and then we said, all right, the next logical question was, what does an atom look like? Give us a model that we can work from. And Dalton had no idea. But he said, it kind of makes sense that atoms are, these kind of singular chunks of material. They might as well be spheres, because that seems to explain how they can be separated and joined and rearranged and all that kind of stuff. So they're little spheres, which was fine for like 100 years. But then as people started doing more and more experiments, especially with electrochemistry, where chemical reactions are producing electric currents, which are caused by moving charged particles, okay, the solid sphere model can no longer explain that. It does not explain where these moving charged particles come from. So, in order to deal with that, the model of the atom goes from being a solid sphere to being a solid sphere that is positively charged and has little negatively charged particles loosely embedded on its surface that can be dislodged in a chemical reaction, and then they can flow through a wire and produce a current. Okay? So it was a logical modification to the model, okay, that then explained data that the previous model could not. All right, everyone kind of following the process? Yes?
Yeah.
Okay. So here's what we need to know then. Okay? Once J.J. Thomson came up with this plum pudding model, okay, it persisted for what would be considered to be kind of a short time. Right? Let's say 35 years or so. Right? Because right around that time, the science of kind of nuclear physics is just starting to take off. Right? And what we're discovering is that while, yes, there are atoms, their structure may not be as simple as this idea is leading people to believe. Right? The main reason for that is that when you have this electrochemistry going on, the positively charged, all the positive charges can't all be one big lump. They must be smaller, separate, individual positive charges based on kind of some of the behaviors that people were seeing. Okay? They were also starting to study radioactive materials that break down, whose atoms fall apart on their own. And when these atoms would fall apart, there wasn't like, the behavior didn't indicate two chunks of a solid sphere. They indicated smaller pieces. They knew these atoms weren't like shattering, okay, but they were breaking down, okay? They were radioactively decayed, right? So people like Marie Curie and Henri Becquerel and people like that, who unfortunately had very short careers, okay, were studying radioactive materials because they didn't realize that radiation is bad for you, right? So they had all these like special rocks in their desk. They were chunks of like uranium and stuff like that, okay, in their desk, right? That's why Marie Curie always looked so sickly in all the pictures of her, okay? Henri Becquerel, same thing, okay? In fact, their desks are in a museum in France, I think, somewhere, okay? And they are still radioactively hot to this day, okay? If you take a Geiger counter, that thing that makes the clicking sounds when something's radioactive, you put it on their desk and the thing goes crazy. Okay? Imagine sitting and working at that desk every single day. Right? It wasn't good for them. Right? They probably went home with a nice green glow about them. So those kinds of experiments indicated that this model doesn't really explain very well how matter behaves at a nuclear level. In fact, this doesn't mention anything about a nucleus. Okay? That's kind of the next logical step, okay, in discovering what the model should look like. So as more and more experiments are done, we're starting to discover that this central chunk isn't one big lump. It's many small pieces, protons and neutrons. So some positively charged particles and some identically sized particles that are neutrons. Okay? Now, that's all well and good in theory, but nobody had performed an experiment that decisively said atoms are not a solid chunk. Okay? Atoms have this nucleus and they're surrounded by electrons. Nobody had been able to prove that. Everybody liked the idea, but there was no definitive proof of it. The main problem being atoms are tiny. We can't resolve them under a microscope. We can't, isolate them and watch their behaviors or anything like that. Somebody had to come up with a way to prove that atoms were, in fact, very small and had a very small, dense nucleus surrounded by other stuff. Okay? So the challenge was devise an experiment that will make this possible. That's where a guy named Ernest Rutherford comes in. Okay? Rutherford was kind of a chemist slash physicist. Okay? And he believed in this idea of the nuclear model. That is that the atom has a central dense nucleus where protons and neutrons reside, and electrons orbit this nucleus. This idea was better because it better explained how electrons could be lost in an electrochemical reaction. Okay? The whole idea of them being stuck to a central big lump, okay, that the solid sphere slash plum pudding idea, it didn't explain that very well for this reason. Electrons are negative, and the solid sphere was positive. What do positives and negatives do to each other? They attract each other. So, if you've got things that are entirely negative and things that are entirely positive, and they're in contact with each other, they're not coming apart. Okay? So the idea that these things could be loosely attached to that central big positive mass didn't really fit very well. Okay? But having them orbit the central mass instead gave a better explanation for how they could come free in a chemical reaction. If they were a little further away and moving very fast, they could be attracted to something more positive and then pulled away. Does that sort of make sense to everybody? Okay? So that better explained that, and it better explained some of the nuclear stuff that was going on at the time. Okay? So Rutherford said, I've got to devise a way to prove that atoms are really, they have a nucleus that's really small. Okay? So, here's what he did. He devised what is now known as the gold foil experiment. Okay, so he took a piece of gold foil, which would have been like tin foil, but made of gold, and even thinner than that. Okay, so if you can imagine like a piece of gold foil that would have had the integrity of like a Kleenex. Okay, so really, really thin, only a few atoms thick. Okay, so he's got this piece of gold foil, and he surrounds this gold foil with a circular fluorescent screen. Essentially, it's photographic film. Now, I know there's a bit of a generation gap here. You guys have probably never used a camera that had film in it. The cameras used to have this stuff in them called film. Okay? And when you would expose the film to light, it would change color. Okay? It would kind of bleach out. So he put this photographic film around here, and then he put essentially an X-ray machine here. And he shot X-rays, which are light, at the gold foil. Right? Now, when he told people this was what he was going to do, they laughed at it. What did they think was going to happen? Like you got a light source and you got something that's solid and you're shining the light at it. What's going to happen? Nothing. Okay? They're like, are you nuts? Like, you know what happens. Like if I put a piece of paper in front of a flashlight, the light doesn't go through. Right? Here, look. Okay? And like it was obvious to everybody else, this is dumb. And he's like, no, trust me. If atoms are really, really small, the light's going to go right through this piece of gold foil. And they're like, how did you get this job? Like, that is the dumbest thing that we have ever heard. He's like, want to bet? Okay. And he sets it up. And he's partially correct. He actually thought all of it would get through. The atoms would be so small and this gold foil was so thin that all the X-rays would get through. Just like they go through you when you go to the hospital and get an X-ray. Right through you. Okay? Well, except the ones that hit your bones. Right? Those ones reflect off, and then that's how you see the bone. Okay? So he's got this set up, and what he finds is that there's a whole bunch of areas of exposure on the film, not just right behind the foil like he thought, or back here where everybody else thought they would end up. Okay? He got them scattered. Okay? The only explanation for that is that as those X-rays went through and hit the foil, some of the X-rays went right between the atoms. Okay? Only way for that to happen is that there is actually a central dense nucleus that's actually quite small, that is surrounded by electrons, which are so small they can't block anything. Okay? And those electrons are likely to be moving very quickly anyway. Okay? Now, electrons are incredibly small. Right? So a lot of the rays go right through, completely unimpeded. Okay? But some of them strike the nucleus of a gold atom. And when they hit it, they're deflected. So they end up like over here. Right? Most of them end up straight through, but some of them get shot off to different parts of the screen. Okay? Proving that yes, in fact, there is a central dense nucleus. Okay? It's there, and it's about yay big, okay, compared to the total volume of an atom. Okay? Everybody okay with that idea? Okay. All right. So, should you know who Rutherford is? No. And his gold foil experiment. He is as important as Dalton. Okay? Dalton came up with the idea of the atom. Rutherford proved the atom as a nucleus. That's like the second most important thing to saying there's an atom. Okay? So saying there's an atom and then proving that as a nucleus, those are the two most important things. Okay? So definitely know Rutherford, know his gold foil experiment. Okay? So he proved that it was a central dense nucleus. Now, you'd think at that point everybody would be happy. Okay, oh, we've just discovered there is a nucleus, it's a big deal, we've been trying to prove that for a long time. Okay, nope, scientists are never happy. Now they're like, okay, so you proved the protons and the neutrons are here, what are the electrons doing? Your experiment didn't do anything about that. And Rutherford's like, they orbit the nucleus. And they're like, okay, where? Everywhere. Okay, so Rutherford's model of the atom actually looked like this. So yes, I've got a central dense nucleus where there's protons and neutrons, and the electrons are all equidistant from the nucleus, and they orbit it like this. Their orbits are just offset a little bit from each other, because what do electrons do to each other? They repel, because they're all negative. So they would naturally set up into these perfectly aligned orbits, okay, and just go around the nucleus in their orbits. And people are like, all right, I mean, they're not like planets, because planets would actually attract each other by gravity. Electrons repel. Oh, okay, fine, that's what they look like, okay? His model didn't last very long. He puts all this effort in, makes a huge discovery. His model lasts like 5 years, okay? Because people then started doing experiments on the behavior of electrons. And what they discovered is electrons can gain and lose energy. And what they knew is gaining and losing energy makes you go faster. If an electron moves faster, it naturally will move further away from the nucleus. Okay? Rutherford's model doesn't explain that. His model said they're all the same distance away, right? And they're not. And in fact, they can jump away and fall back, jump away and fall back. Okay? And his model couldn't explain that. But his buddy, Bohr, could. Okay? The boring world of Niels Bohr. Okay? Studying the arrangement of electrons around the atom. Okay? So what Bohr discovered was, yes, electrons repel each other, and as such, there are different orbital levels, like planets around the sun. Okay? They can't have the same orbit, or they can, but they have to be on opposite sides of it because they would repel each other. Okay? So he devised what we call the Bohr or the planetary model of the atom, which is still to an extent accepted today. Because if you were to take a picture of an atom and freeze it in time, you would probably see something like this. The problem is an atom is never frozen in time. An atom is constantly changing. Okay? And so thus, the electrons are never just in this spot. Okay? There's an area where you're likely to find an electron based on its energy, and it's not a perfect circle. Okay? In fact, basically no orbitals, okay? I say orbitals, not orbits, okay, are circular. Right? An orbital is an area where you are statistically likely to find an electron based on its energy, and they can have a whole bunch of really funky shapes. Okay? So Bohr's model, generally accepted, but isn't our current model of the atom. Okay? But it did explain the different energy levels that could be possessed by electrons. What it didn't explain was their ability to jump from one level to another. Okay? He said it was fixed, okay? And we now know it's not. In fact, we know that because plants can carry out photosynthesis. Okay? And you might be thinking, how does Coderre tie those two things together? Here's how. When light strikes the chlorophyll molecule in the leaves of a plant, the electrons get excited. They gain energy, they move faster, and they jump from low levels of energy that are near the nucleus to higher orbitals or levels of energy that are further away. When the sunlight is gone, the energy that's holding the electron up there is gone. So the electron falls back down to a lower energy level and releases the energy it gained from the sun. That energy is then captured and used to break carbon dioxide and water up and make sugar. Okay? The energy for making sugar in photosynthesis comes from jumping and falling electrons, okay, that are excited by the sun hitting them. Okay? The same thing goes with glow-in-the-dark materials. Okay? If you've seen any of those things and you put them out in the sun for a little while, then you put them in the dark and they glow for a short time, same deal. Okay? When you put them in the sun, the electrons gain energy and jump away from the nucleus. When you take them out of the sun, those electrons fall back to lower levels and release the energy they gained from the sun as light, and they glow in the dark for a short time. Okay? Not usually for all that long, but for a little while. All right, so our current accepted model of the atom, the currently accepted model of the atom is what we call the de Broglie or Electron Cloud model, also sometimes called the quantum model, but we'll call it the Electron Cloud or de Broglie model. Okay, and it explains this ability of electrons to jump around, okay, to move around within the area of the atom. Okay, now, one of the things I'm going to ask you to be able to do here is to draw me a picture of an atom of my choice. Okay, in fact, that will be a question on your unit exam. Okay, I'll pick an element and ask you to draw me a picture of what its atom looks like. Okay, so what I'm going to want to see is a picture of the electron cloud model with the right number of protons, the right number of neutrons, and the right number of electrons all in the right places. Okay, so we're going to go over right now how we would do that. Okay, so let's say I want to draw an atom of beryllium, let's say. Okay, that's a nice simple one. How do I know how many protons to draw?
It says on the table.
Right, which number tells me the number of protons?
4.
Right. The atomic number, and you're going to get a periodic table, okay? The atomic number tells me the number of protons. In a normal atom, because an atom is neutral, the number of protons is equal to the number of electrons. The positives and negatives have to cancel each other out. So that number tells you two things. It does not tell you the number of neutrons. How do I calculate the number of neutrons? Yeah, you subtract. Well, not from the neutrons, but you actually subtract the number of protons from this number, from the atomic mass. Okay, so my atomic mass here is 9.01. I subtract 4, I get 5.01. Now I'm not going to have 0.01 neutrons. How many neutrons do I have? 5. I just rounded off. Okay. All right. So I've got to draw an atom that's got 4 protons, 5 neutrons, and 4 electrons. Okay, so I'm going to have 9 particles in the nucleus. All right, so there's my nucleus. Should I indicate which ones are neutrons and protons? Yes. If you don't, you'll lose a mark because you didn't tell me how many protons and neutrons there were. Okay, so 1, 2, 3, 4. All right, so there's my 4 protons. The other ones are neutrons. And where do I draw the electrons? Around it, yeah. 5 out of 5. doesn't have to be a work of art, okay? I indicated this is the electron cloud. The electrons, 4 of them, are in the cloud. There's my 4 protons, my 5 neutrons, done. Okay, there's a picture of our currently accepted model of the atom of early. Okay, questions on that? Okay, so the really only tricky part of that is calculating the number of neutrons, okay? And that's just atomic mass minus atomic number. Okay, any other questions there? All right. So, Rutherford and Bohr would have kind of accepted this picture of the atom, okay, that central dense nucleus, but you can see the electrons are offset from each other. There's different energy levels, but they're offset, okay? Our currently accepted model still looks like the electron cloud. Now, the electron cloud is not random. Things are not just randomly dispersed in this cloud. They could actually be found in these things called orbitals, okay, which are energy levels that electrons can be in. Right, so you got the nucleus here in the center, and then you got your first orbital, which is called 1s. Okay, that would be the lowest energy. It's kind of a sphere around the nucleus. Okay, then you've got your 2s orbital, which is a larger sphere around the nucleus. Then you've got your 2p orbitals. Okay, they're kind of teardrop shaped, and they can be dispersed kind of equally around the nucleus. The 3s orbital is spherical but bigger, and then they get crazy after that. It goes up to like 5 or 6p, okay? And these things get crazier and crazier shaped. In fact, there's one that's shaped like a donut that goes around. I can't remember what number it is, but okay, they have all these weird shapes, and they're all based on energy, okay? The higher ones contain the highest energy electrons that are furthest from the nucleus, okay? Are you ever going to need to know the 1s, 2p? No, you're not. Well, Chem 20 you will, but not in Science 10, okay? Just kind of know it's not truly a random cloud. Okay, it's an area where electrons can be found based on energy. All right, other thing we talked about yesterday. So Dalton said that the atoms of one element are all identical. The atoms of different elements are different. Okay, that is true. And it's also what determines the properties of each element. Okay, so if I'm looking at a lump of sodium, okay, sodium is a soft, silvery, highly reactive metal. Okay? Its atoms contain 11 protons, 12 neutrons, and 11 electrons. Okay? The properties of sodium are based on the number of protons in the nucleus. Okay? So you have an atom that has 11 protons, it will have all the properties that sodium does. Okay? The number of protons determines the properties. Okay? If I'm looking at an atom that has 8 protons in the nucleus, I'm going to be looking at a clear, odorless gas, oxygen. Very different properties because its atoms are different. They have different numbers of protons. Okay? So that kind of goes along with Dalton's second point. Okay? The atoms of one element are identical because they all have the same number of protons, so they all have the same properties. Atoms of different elements are different because they have different numbers of protons. So this underlined part here, it's important. Okay? Elements have different numbers of protons in their nucleus, and those differing numbers of subatomic particles influence the properties of different elements. Okay? So make sure you got that underlined or highlighted in your notes or written down or whatever, because that's something that could possibly come up on a quiz like on Thursday of next week, when you will have your first quiz. Okay, anybody still need that? All right, in your worksheet package, okay, so if we go to Google Classroom and we go to okay, in the class work tab, the worksheet packages, that's where you need to go, and you need the one for chemistry. You will find these 12 questions. Okay, and they're all about the stuff that was in this lesson here. Okay, that's the kind of stuff that will end up on Thursday's quiz of next week. Right, so what I would like you to work on here now is these 12 questions. Good thorough, complete sentence answers. You got the rest of the class to work on that. Okay, if you don't finish it, try and have it done for Tuesday. Okay, because we're going to go over start class on Tuesday. You may. All right, you don't obviously have to write down the questions because you have the questions in your worksheet package. If you want to just write them in on your phone from here, or you want to write them on a separate piece of paper, whatever works for you, I am totally fine with it. Okay, but you got, what, 24 minutes or so, okay, to do that. Yes, but this isn't going to be coming in for marks. I just want you to have it done so that we can go over it together.
So we can do this one.
Paper.
Yeah, absolutely.
Oh, I can't. What do you mean? Like not like the last
For the worksheet. Yeah, or a worksheet.
Oh.
Oh, thank you.
Chemistry.
Hey guys, if you got questions or you're having trouble, just let me know. Okay, guys, nobody should be packing up. Everybody's done. Night. Have a good weekend, but not too good. Listen up to this one, please.
In the name of the Father, and the Son, and the Holy Spirit. May the Lord bless you and keep you. May the Lord
Guys, listen up to
and
this.
find God and grace with you. May the Lord look upon you with favor and grant you peace. In the Father, and the Son, and the Holy Spirit. May a wonderful, blessed, long weekend.
See you guys on Tuesday.
But there's like the apartments, you know, the houses, it's like behind that. Yeah. The grass spot.
Did not know what to do. Made this like power, like we actually stacked it right